Hello everyone, this is Sukruti Joshi from LG Institute of Engineering and Technology, Ahmedabad. I am going to take the video lecture series on chemistry. The subject code for chemistry is 311001. Till now, in this particular subject, we have studied different analytical techniques. In chapter number 8, which is analytical techniques, we have studied about conductivity meter, we have studied about potentiometer, pH meter. After that, we have started the part which is very important for us, which is spectroscopy. Spectroscopy involves the interaction of light with matter. With the use of this particular principle, we can identify any kind of matter, whether it's solid, whether it is liquid, whether it is gaseous. So we need to make sure here that we have to use the phenomenon, the principle with which we can actually analyze our own sample. Right? So here we can utilize two different phenomena, and depending upon that we have two different types of spectroscopic methods available. First one is absorption spectroscopy, while second one is emission spectroscopy. Right? We have another kind of spectroscopic methods also. For an example, scattering phenomenon. For an example, reflection. Another one can be photoluminescence spectroscopy. Right? These are the things which actually forms the principles, the basics of spectroscopy. And to measure any kind of sample through spectroscopy, two things matters most. Number one, which is the region or the region of electromagnetic spectrum which is used there. And number two, the matter, that means how the matter behaves. That thing plays a very important role here. Okay? Now, let's see that what is an absorption spectroscopy. So, an analytical technique which concerns with the measurement of absorption of electromagnetic radiation is known as absorption spectroscopy. As I said you earlier, each and every element is individualistic in nature. Along with it, their difference or their energy difference between the state is also different. Now when the energy difference is different, then at that time the light that is absorbed will also be different. And in that manner we can identify that particular sample. This is the base of identification of any kind of sample. Now let's say for an example, UV, that is ultraviolet range, will move from 200 to 400 nanometers. Then we have visible region, which will ranges from 400 to 800 nanometers. Depending upon that, it is known as UV visible spectroscopy. And we have IR. IR ranges from 1 to 1000 micrometers. Here, the UV and IR spectroscopy are absorption spectroscopy. But when we talk about another one, that is at atomic base, these are molecular spectroscopies which identifies the molecules. Okay. When we talk about atomic spectroscopy, we can refer it as AAS. AAS stands for atomic absorption spectroscopy. These are the absorption spectroscopic methods. Now let's see that what are the emission spectroscopic methods. So emission spectroscopy is an analytical technique in which emission either of a particle or of a radiation is dispersed according to some property of the emission, and the amount of dispersion is being measured. Right? The thing is the emission phenomenon that plays an important role here. So, if we want to take an example of it, we can take an example of AES. AES stands for Atomic Emission Spectroscopy. Right? This is again a very basic atomic spectroscopy, which can detect any kind of metal, any kind of non-metal, any kind of heavy metal also. And these spectroscopies are very beneficial for us as they can determine the samples at very low level, even at nano level also. They can detect the particular sample. If your instrument is advanced instrument and updated instrument, then you can analyze your sample at your nano level also. A very minute amount, a very minute size, but that can get precisely detected using these two spectroscopic methods. Let's begin with the first one, which is known as UV visible spectroscopy. UV visible spectroscopy works on the principle of absorption, and therefore it is also known as absorption spectroscopy. So basically, UV visible uses the range of electromagnetic spectrum, which is known as UV and visible. UV will ranges from 200 to 400 nanometers, while visible will range from 400 to 800 nanometers. So when we use the word UV vis, at that time it will range from 200 to 800 nanometers. Now, certain samples are colored in nature, certain samples are non-colored in nature. The samples which are non-colored in nature can be detected using UV. If it doesn't show any kind of color, and if it is present in very low levels, then we can detect it using UV. If the sample is colored in nature, then we can analyze it through visible range. That means we can get an idea of that particular sample, a qualitative or a quantitative analysis done using the visible range, because in visible range we can observe that color, and in visible range they will show you. Right? Each and every element has its own tendency to absorb the light. Right? They will not absorb the light in each and every particular range. Certain samples absorb in certain ranges only, and that's why they are known as individualistic sample or individualistic matter. Okay, now let's begin with the principle of UV visible spectroscopy. Okay, it gives you an idea that how it works and why the samples get analyzed in UV. So in normal condition, the electrons remain in their ground state. When it is imparted with certain kind of electromagnetic radiation, at that time it absorbs the radiation and moves from ground to excited state. Now if this absorbance is in the range of UV, then this type of spectroscopy is known as UV visible spectroscopy. The instrument is known as UV spectrophotometer. The spectra is known as UV visible spectra, and the technique is known as UV visible spectroscopy. These are the things that we need to make sure when we move ahead with this. The basic principle of UV is Beer-Lambert's law. What Beer-Lambert's law called, or how it will give us identification. So two scientists are there. Number one, scientist named Beer. Number two, scientist named Lambert. Both of them gave the principle of UV visible spectroscopy on their own. And afterwards, after certain research, it has been decided that we can actually combine them together and make one particular system, which is known as Beer-Lambert's law. So when any kind of monochromatic radiation is passed through a solution, the absorbance of radiation is directly proportional to the concentration of the sample and to the cell length, which is used as a sample cell. Right? Two things are important. Number one, concentration of the sample. Number two, cell length of the particular sample tube. So we can denote it as capital A is equal to epsilon into C into L. Here A is the absorbance. C is the concentration of the sample, and L is basically length of the sample cell. Right? When we put all the values in this, we can get the absorbance in nanometers. Now let's move ahead to the instrumentation part. The instrumentation is also known as block diagram. It is also known as flow chart. It can be denoted as I show you in the image. Here the UV radiation region extends from 200 to 400 nanometers, and the visible radiation region will extend it from 400 to 800 nanometers. So what you need to make sure that we have a whole range, that is 200 to 800 nanometers. Now let's begin with the instrumentation part. We have light source. From light source, the light is imparted on monochromator so that we can get a monochromatic light. That monochromatic light will move further to the splitter so that it gets splitted in two different directions. One way goes to sample tube, another way goes to reference tube, because we need to match them, we need to refer them. Okay, so for reference we have taken a reference material over there, so we will take it into that. When they move from that, they lastly goes to the detector and recorder, right? From light source, whatever light we have given it and whatever light will be moved out from that, that will be totally counted here, and that depends upon two things: concentration of the sample. If it is higher, the absorption will be obviously higher, and if the cell length is higher, along with that the absorption also will be higher. The sources are required here to scan the entire UV visible band. Generally, it is a tungsten lamp which covers 330 to 700 nanometers. As with the dispersive IR, the lamps illuminate the entire band of UV or visible light. Here the monochromator, which can be a grating or a prism, gradually changes the small bands of radiation sent to the beam splitter. The beam splitter sends a separate band to cell containing the sample solution and to the cell containing reference solution. Now, if we move further, the detector measures the difference between the transmitted light through the sample versus the incident light, that is I versus I0, and sends the information to the recorder. Right? This is the way how it will move further. Okay? This is all for this one. Next we will see in our next session. Thank you so much everyone.